So this talk is going to be about learning distributions from a Boolean function analysis point of view. So just so that we are all on the same page, I'll just write down definitions of some Boolean functions which are going to be of interest during this talk. It's going to take a couple of minutes. So just so that all of us are on the same page. So we're going to consider Boolean functions on the hypercube, meaning functions which map -1, 1 to the n to 0, 1. And the functions, the classes of functions we'll be interested in will be the following 3 or 4 classes. One is degree D polynomial threshold functions. Okay. So these are just functions which are of the form f equals sine of a polynomial, where p is a polynomial, p minus 1, 1 to the n to r is a polynomial of degree D. Okay. So this is what is meant by a degree D polynomial threshold function. You're taking a polynomial and then you're taking a threshold on it. Degree, when D equals 1, these are called linear threshold functions for obvious reasons, and or alternately half-spaces, and they will be occupying a majority of the talk. Apart from this, we'll consider DNFs, or which are just ORs of ANDs. So something like x1 and x2 bar and x3, or something like this. Okay. And CNFs, which are ANDs of ORs. Okay. So, sorry, in -1, 1 to the n here. Oh, it doesn't matter. It's not that I'll associate a semantics with it. 0, 1 is, well, 0 is false, 1 is true. Okay. So I guess all of you are familiar with this class of functions. Nothing to do here, but okay, good. So there has been a lot of work on learning functions. There are a lot of learning theory work on learning, a lot of work on learning functions. Somewhat, the work has been somewhat disjoint in the sense there has been some work from the complexity theoretic aspect. There has been some work on the learning theory from the complexity theoretic point of view. So from Boolean function analysis and learning on uniform distribution, and somewhat disjoint set of techniques and somewhat disjoint set of techniques have been employed in the machine learning community. Okay, so I guess my first excellent. This works. Excellent. Okay, so learning functions, two kinds of work: Boolean function analysis / complexity theory, or complexity theory, and another has been machine learning, and they have been somewhat, this set of techniques have been disjoint. Okay. As far as learning distributions go, so most of the work here has been from the point of view of machine learning or statistics. In fact, learning distributions in statistics predates learning functions, or even before learning was formally defined in computer science. So various problems like learning Gaussians or density estimation or parameter estimation, inference, these were considered much before computer science, or much before theoretical computer science existed as a discipline. So just to give a flavor of the kind of work that has been done on learning distributions in this community, with its intersection with computer science. Of course, there's tons of work here, so I can't really discuss that, but there's been tons of work in learning distributions from the ML point of view, ML's intersection with computer science. So in TCS, there's been a lot of work here. So just to give a flavor, say learning Gaussian mixtures, which is like, so I'm not naming all the authors, Dasgupta, Arora, Kannan, Vempala, Moitra, Valiant, Belkin, Sinha. There's been a lot of work topic models. So Aurora, Kannan, Moitra, Kakare, population recovery, RV, and I forget all the other authors. And of course, I'm not even mentioning the tons of work that has taken place in statistics on learning distributions. Okay. However, here, like take learning distributions from a Boolean function analysis / complexity theory point of view, there hasn't been much of work. So in a sense, learning distributions from a complexity theoretic point of view, complexity theory, so learning distributions hasn't been put under the scan of complexity theory really a lot. And this is what I intend to discuss in this talk. Okay. So, okay, now I guess. Okay, so what do we mean by learning distributions from a complexity theoretic point of view? So learning distributions means, of course, you can't learn arbitrary distributions. So you have to define some suitable notion of low complexity distributions and then discuss how do we learn these low complexity distributions. So the challenge really is to first define what are appropriate classes of low complexity distributions. Okay. So what's the simplest possible, so we are considering distributions on the hypercube now. What's the simplest possible distribution on the hypercube? Okay. I was looking for some other answer actually. I was going to say the uniform. Okay. Let's say, okay, a point mass is, of course, is very simple. It's not simple from my point of view. So I'll say let's go for uniform. Okay. So uniform distribution is certainly a very simple distribution on the hypercube. Okay. So now we'll generate low complexity distributions by massaging these uniform distributions. Okay. So one way of generating low complexity distributions is that the generation process is very simple, meaning that there's a circuit C which maps n bits to m bits. Okay. There's a circuit C which maps n bits to m bits, and this circuit C is very simple. So one of the simplest ways I can think that C is very simple is that every output bit is a function of only order 1 input bits. Okay. So just think of order 1 as 3, let's say. Just think of order 1 as 3. Okay. So we are considering a circuit C where every output bit is just say a function of 3 of the input bits. Okay. So this is the graph of the circuit, and you feed in uniform bits here, uniform in n, and you get some distribution here. And this is one way of saying that distribution is very simple. It's generated by a very low complexity process. It's a function of only order 1 input bit, let's say 3 input bits. So any kind of gates is fine. Like, I mean, you can let's say and or and not. All gates, okay. All gates, yeah, all gates, all kind of gates. I mean, well, it's only order constantly when input bits. You can simulate anything by the other with a constant overhead, so it doesn't matter really. Okay. What about the complexity of learning such distributions? Okay. Exactly. I'm going to come to that. Okay. Okay. So, yeah, I'm going to come to that. Okay. So the point is that the reason even this class of distributions is very hard to learn. The reason being that this class of circuits, so see, the output can be pseudo-random. The output can be pseudo-random, can be cryptographically pseudo-random. So it's hard to distinguish it from random. So you can't even, being given such a distribution, it is impossible, it is cryptographically hard to even distinguish it from the uniform, leave alone learning the distribution. Of course, this doesn't constitute a formal proof that it is hard to learn, but under like cryptography is in NC0. So Goldreich one-way function, but cryptography is NC0, so you can generate some. You can generate cryptographic. You can generate pseudo randomness here. Yeah, the input is uniform. So the input is uniform on n bits. This is a circuit C, and the output. So the output here m might be n square. Okay, so m might be n square. So now the output, of course, is not uniform. It's very far from uniform. It has only n bits of entropy, or maybe even less. But it's cryptographically hard to distinguish it from uniform. So you can't even distinguish it from uniform, leave alone learning this distribution in any reasonable sense. This doesn't constitute a formal proof. Anyway, as Orr said, this kind of a model was considered in a paper from '94 by Kearns, Mansour, Ron, Rubenfeld, okay, Shapiro and Selly. This is a long author list. And they kind of gave the same reason of so why this class of distributions is very hard to learn. Okay, so the moral of the story, what I'm trying to say here, is that even if the circuit C is very simple, this kind of way of generating simple distributions, you don't get very far as far as learning is concerned. Even this is very hard to learn. So certainly there is no sweet spot here for. There's no set of interesting questions, or there doesn't seem to be a set of interesting questions here. Maybe there's a set interesting question. I don't know what it is. Okay, so let's consider some other mode of generating simple distributions. Okay, I guess the drill is. Okay, so what is the other mode of generating simple distributions? So one other mode might be that.
So to learn here would mean that I would know with high probability the output of a random given.
No, okay. So this is a good time for me to say what is exactly learning in this context. So you have to learn the distribution, not really the function. So learning a distribution, learning D. Let's say a distribution, learning a class of distributions, learning a class C of distributions over -1 over 0, 1. Okay, you can consider 0, 1 to the n. Means that the learner, the algorithm, gets, let's say, polynomially many samples, Polyn samples from an unknown distribution from D belonging to C. So the learner doesn't know what distribution it is, it just belongs to this family. The learner gets polynomially many samples, and then after this is supposed to out, and running in polynomial time, is supposed to output description of circuit C prime. So this circuit C prime is also of polynomial size. It's supposed to output a circuit C prime such that no, need not belong to C. So of course you can consider different kinds, belongs to C, doesn't belong to C. The algorithm is efficient, so C prime has to be a polynomial size circuit such that if so C prime, let's say C prime maps some poly n bits to n bits such that C prime when C prime is fed with uniformly random bits, T uniformly random bits, then the output distribution differs from the unknown distribution by epsilon in L1 distance or statistical distance. So this is the notion of pack learning in this model.
It means that those pseudo-random things are trivial to learn because you just have to generate something that looks random.
No. This is total variation distance. Pseudo-random and random doesn't look close in total variation distance. So you have to generate something. Yeah.
In this model, if the graph is a random graph, sparse random, right? The gates are threshold, then, and if you assume UN is sparse, so sparse uniform, not uniform.
Okay.
Then the 8 can be learned from our recent paper.
Oh.
We study exactly this.
So with what are the parameters here? Like you're saying, like
say n to m any say reasonable yeah, and but the graph should be sparse, whereas say root n only has root n degree.
only has root n degree in which sense? Like
Smaller.
Here it's even more sparse.
Even more.
But what you need is that the uniform is supported on a sparse number of bits.
The input distribution is not even, it's uniform sparse distribution. So
oh, the input distribution is not uniform.
No, it's not uniform.
it's uniform k-sparse.
Okay.
It's very different. I think it's very different because there is not, well, don't think we expect statistical random. You can tell it apart from random just by sparsity. Like you put in sparse to get out sparse, it doesn't look right.
Sorry.
No, not at all. Thanks. Okay, so we have defined what the notion of learning a distribution means here. Of course, sometimes you may not be able to do it Polynomial samples and polynomial running time, so maybe quasi-polynomial, whatever you can do. Okay, so we converged that it seems that one mode of generating simple distributions, you do not get any interesting. It seems we do not get any interesting learning problems. So let's consider some other mode of generating simple distributions, and here we'll see there are interesting learning problems. So what is the other mode of generating simple distributions? So you start with the uniform and then we'll apply some low complexity filter on the distribution. Okay. So one the first model we considered there, the generation process was simpler. Okay. The first process here, the generation process, was simpler. Now we are going to supply some filter which is low complexity. Okay, so meaning this, that there is a circuit C, it's fed in the uniform, it's fed in uniform random bits, and so it's fed in some input x, and what the input only comes out if Cx equals 1. Okay, so you reject depending on whether Cx is 0 or 1. So what you get as the output distribution is a uniform on what the output distribution you get is uniform on C inverse 1. So you get uniform on the satisfying assignments of C, where C is a low complexity circuit. Okay, and so this is the kind of meta class of distributions we'll be considering learning in this talk. Okay, and as we'll see here, there is somewhat richer structure. Okay, so first let's try to do the same thing. Suppose C is low complexity. So let's think of the simplest low complexity function I can think of. So we'll only be considering Boolean functions here. Suppose C is an MC0 function, meaning C is a function of only 3, let's say 3 of the input bits. Is it easy to learn this distribution then? Yes, because, well, there will be only 3 input bits which are non-uniform, so you can just learn it n cube. Well, so in particular, if it's a k junta, you can learn it in time n to the k. Okay. So what's the next? Okay, so now is the time that I describe the results. So the results are as, oh sorry, I should have mentioned this in the beginning. This is joint work with Ilias, Diakonikolas, and Rocco, Servedio. The results are that.
But here, if C is just a C and F or something, you don't even know if this is empty or not.
No, but
No, you get some random satisfying assignment.
empty, there would not be sample. But he's going to describe.
No, you get random satisfying assignment. So you,
That's what you
of
get.
course,
But I still wonder what.
yeah. So the
Probability is hard. Should mean something also here, right?
it will mean something here. It will mean something here. So I'm just going to just write the results now.
When you're going to talk about the polynomial is the number of input x's or the number of output x's that you're going to be counting?
Now the same.
They're all the same. We have assumed.
We have only output when the
No,
when
no,
it
that's
says
the
when if x is
condition.
1.
Yeah, but you output the inverse image, right? You are uniform on all the things.
Yeah, but the sampling technique is you might have only a logarithmic number of samples, getting like you can put n x's and get only log n of x's that satisfy C of x is equal to 1.
Maybe yes.
But
Okay.
it's length n. The
But of
length
length n.
The length doesn't.
You get the
Okay.
Uniform on C inverse.
Okay. So
One output read to C.
okay. So let me write down the distribution for a specific. If this is C, if
One output.
then the distribution we are considering D, the distribution will be considering corresponding to C will be uniform on C inverse 1. Okay. Okay. Sorry, this picture was very misleading. Sorry for that. Does that make sense? So yeah, maybe C only accepts logarithmically many inputs, but that's fine. It still makes sense. Am I making sense?
So you're going to be counting in based on this number of inputs.
I'm just going to consider the input length. I'm just going to consider the input length.
But you say your definition of learning was a number of pulling n samples.
Yeah.
The cost of getting a sample is you have a black box that generates a sample from this distribution, u of c minus 1 of 1. It doesn't cost you any.
Yes, okay, that's what I was asking. So you have a black box, and you have as many, n is the number of samples from this distribution.
No.
Not the number of samples.
N is the input. N is like the string length of the sequence. N is the length of the sequence.
Okay. The distributions are now on n bit strings.
Distributions on n bit strings. Okay, so yeah,
So poly n is the number of samples from this distribution.
poly n is the number of samples you expect to get from this distribution. Poly n or
Maybe repeating if there is only one element in the
if there's only one element, you will keep getting the same sample. It's trivial to learn it.
You know, it might be a distribution for which it's actually hard to get poly n number because
Yeah. So it's not that the sampling process necessarily needs to be. I mean,
So to generate this black box is very hard.
then generating this black box might be very hard. Generating this black box might be very hard. You're correct. Generating this black box might be very hard. Okay. So the results are that if the class of circuits if the class of functions we are considering here is half spaces or linear threshold functions, then there is a poly n over epsilon time algorithm for learning this class of distributions.
So if
If
C is a half space,
C is an unknown half space and what you are getting is the satisfying assignments of an unknown half space, you can learn this distribution in time poly n over. You can learn the distribution which is uniform on this unknown satisfying assignments of this unknown half space in time poly n over epsilon.
Suppose you want to write for half spaces.
Sorry. I think I should rewrite this line so that it makes half spaces. Okay, poly n over epsilon, poly size DNFs n to the log n over epsilon. The number of samples, the running time, both of them. Okay, so the number, I'm not distinguishing between the sample complexity and the running time. As Noga said, CNFs, in fact, even monotone to CNFs, so even a smaller subclass. Hard. Well, hard depends on like the cryptographic assumption you're willing to use. If you assume sub-exponential size unique signature schemes, it's exponentially hard. So, but cryptographically hard. And same with, say, intersection of half spaces slash degree 2, or even like let's say degree 2 PTFs, degree 2 polynomial threshold functions, again hard. Sorry? Intersection of two half spaces. Okay. So kind of, okay, the moral of the story of what I've written here is that in all the cases where it actually is, in the cases I've written here, the cases where it's hard to generate this circuit like for CNFs, the rejection, this sampling process is actually very hard to construct a black box. The black box itself is like a hard to construct circuit. It's in fact again hard to learn these distributions as well. No, this is not a general principle. I'm just saying it. Yeah, no, this is not a general principle. Of course, unique satisfiability is hard to generate, but it's easy, trivial to learn. But at least in the process I've written here, CNFs, it's hard to generate. It's hard to generate this black box with samples according to satisfying assignments of a CNF, and it's hard to learn. Same with monotone to CNF. Same with intersection of half spaces, or even degree 2 or higher polynomial threshold functions. I have an example. It's hard to generate, easy to learn. I can give you an example. There was an example in the somehow something like a noisy parity, something based on the noisy parity. So are we something like a noisy parity? Like suppose I tell you that the distribution I'm generating is based on noisy parity. So of course I can generate the distribution very easily, but you can't learn the distribution of noisy parity. And yeah, the other way, unique satisfying assignment, even somewhat more interesting example is that of graph isomorphism. So if I give you, suppose my satisfying assignments are automorphism of a graph. It's hard, it's not hard as in cryptographically hard, but it's hard to generate automorphisms of a graph in the worst case.
Well, it depends as what. Not an isomorphic graph is easy to generate, but a permutation that's in the automorphism.
Oh, sorry. That was not what I intended to say. That's not what I intended to say. Okay, you know what? Let's not get an example. Like, yeah. Yeah.
So are the hardness results again proper learning or against
Any learning. The circuit that you need to output need not be like don't need to necessarily give out a half space or give out a CNF or a DNF. Any kind of circuit is hard to learn. Okay. Most of the time I'll be spending on these two results. Really, the first result, the latter. The hardness results are somewhat very easy actually to prove. Once you have the right thing, it's not hard to prove. So I'll maybe spend 10 minutes towards the end about the hardness results. Let's discuss the algorithmic results.
The output bit is only one bit, right?
The output is only
one output bit. So
no.
So in all this,
Sorry. No. So
the distributions are on n bits.
the output.
The output is n bit also, but you output it only C of it is 1. So you look at all the
The circuit. I mean the output of the circuit is only one bit.
the output of the okay. Should I again write down the model?
So you want it there. It's just that your picture is.
This is the source of all confusion.
You have no picture. Yeah, there is some circuit, some Boolean circuit, simple Boolean circuit.
There's some hidden simple.
With just Boolean says 0 or 1, and the distribution is defined is the pre-image of the 1.
Yeah, so you should have x equal, and then half of it is where C is.
Excellent. 0, 1, and what you are getting, this is some unknown circuit, so there's some unknown partitioning of the space. What you are getting are samples from this half uniformly at random, and you need to learn this distribution. You may want to learn this partition itself, you may not, depends on you.
Okay. So are there any results from the statistical learning literature where they're assuming they're getting only positive examples for classification and they're actually trying to recover the set?
I don't know, but I'm not familiar with the literature either. Like, I don't know. I'm not the right person to ask. I don't know. Not that I know of. I don't know in statistics like how the Boolean function. Somehow there's a key notion of it's being generated according to satisfying assignments of Boolean functions. I don't know why it would be interesting necessarily, but I don't know. Yeah, you can think of a smoother version of this. So you're getting samples from a level set of a function of this is not, and you're trying to learn this distribution. Yes. I do not know of the work, but maybe there's work. I don't know. Oh, sorry. Okay. So, most of the talk, or for next substantial part of the talk, I'll be discussing the result on half spaces. Okay. So now let's see, what are we asking? We're saying this is the hypercube. There is some unknown half space. Okay. You are getting random points from the positive half of this half space. Call this half space F. And you want to learn this distribution. You want to produce a circuit which can efficiently sample from this distribution. Okay. So, of course, you don't need to learn the half space, but in a sense, you have to learn the half space, right? Okay, so I'm now describing the algorithm. Okay, so you don't need to learn the half space, but essentially, you do need. You will have to learn the half space F in some sense. Yes.
Sorry for that. So, do you require the learning algorithm to output a distribution that is exactly the distribution?
No, I said epsilon. So epsilon closing statistical distance. Okay. So you need to learn the half space F in some sense. Okay, the hidden half space F in some sense. First of all, what sense do you need to learn the half space F in? So there are two questions. It seems necessary that you need to learn the half space. You need to learn F if in some sense, and second question is, what do you do after you learn? Because after you learn F in the appropriate sense, because the point is you don't want to learn F, you want to produce a circuit which samples from uniform on F inverse 1, right? Okay.
Didn't we pin down already what he meant by learning? Yeah. No, but what it means by learning D. But he says that D is a distribution and learning D is pinned down. But learning F is
a function. I mean, you need to learn F in some sense. What is the error? What is the distribution? What do you mean by learning F here? And secondly, even if you learn F, you want to output the distribution. You want to output a circuit for the distribution, not F. So, what do you do after you learn F? Okay. So for yes.
So just I can think of a way I would do that, but it would be totally unrobust if somebody would start to hide just one x that's actually not for which C of x is equal to 0 in the sample I'm given. Are you going to do something which is robust to this kind of thing?
It might be able to tolerate, like, inverse of that amount of noise, but nothing much more. I don't think the process is at all robust to noise. Yeah, I mean, but trivially there's something, but nothing more than trivial that I know of. And you will see why, because they'll be like, you will see why it's not robust to noise, or not that I know of it's robust to noise. Okay. Okay. So let's try to answer the second question first. So forget about learning F. Even if I give you F, okay, even if I give you F, you want to output a circuit which samples from uniform on F inverse 1. Okay. Is that process easy or hard? Can this be done? Before the paper was written, it was hard. Okay. So actually, it's a good point to introduce, and I need this machinery anyway. So basically, now the problem we are first considering is, suppose I give you a function half space F, and I ask you to generate uniformly random points from F inverse of 1. How easy or hard it is? So of course, if F is dense, meaning F has, say, at least inverse polynomial fraction of points of the hypercube, you can just do rejection sampling. But what if F is sparse? F has only 2 to the minus n over 10 fraction of points. Then what do you do? And the answer is provided, well, in a series of, actually this was the first paper, Ben Morris and Alistair Sinclair, who used, they used Markov chain Monte Carlo method sample from uniform on F inverse 1. It's a pretty involved paper, I don't know the proof fully. Next paper was by Martin Dyer, who used, actually very simple and very elegant paper, dynamic programming plus rejection sampling. And since then, there also have been deterministic kind of, not deterministic, of course you can't do sampling with determinism, but No, no. It's not a convex. It's hypercube points. It's points on the hypercube. Two half spaces. Intersection of two half spaces is it's hard. So, okay. So this is a fair amount of machinery that goes here. I do not know the proof. Basically, you consider the obvious Markov chain here to sample points from a half space. Proving that the Markov chain has a polynomial mixing time is a tricky detail, is a tricky thing. But this is actually very simple, very elegant paper. But what I want to say is that certainly the following is true, that if I give you a half space, you can sample uniformly or close to uniformly from satisfying assignments of a hidden half space. So certainly the machinery that will require is at least this complicated. What I want to say is, okay, this is required, and as we'll see, this is kind of the key step. The fact that you can sample from there's a learning algorithm for half spaces and not for CNFs. Kind of this is the key step, that there is something from that given a half space you can sample from you can sample satisfying assignments, but given a CNF you can't sample satisfying assignments. In some sense, this is the key distinction between the easiness and the hardness results. Yes.
What are the dates on this type of works?
This is 99. This is 2003. Okay. Okay. So we have said, okay, suppose I give you a f, or suppose I gave you the f, or maybe a super close approximation to f. Then you can employ one of these algorithms and sample from f inverse of 1. So that means given f, you can certainly give the polynomial size circuit to learn this distribution. So now we need to learn f. We need to answer the first question. Okay. Okay. Time for the drill again. Sorry? The Dyer thing? I can describe it in 2 minutes, or no, maybe not 2, but let me try anyway. Can I just do it without writing? Let me try without writing, without giving too many details. So again, what is the key problem in sampling things? You could have done rejection sampling if the function was dense. So now you want to somehow somehow you want to do this way. If you could have gotten a handle on on some particular part of the hypercube in which f is dense, then you would have been done. Okay. So what Dyer does is he says, if half space was such that all the weights of the linear of the half space were all polynomial sized integers, then you can sample using just simple like dynamic programming. It's the same reason why knapsack can be solved if you have polynomially large weights. If the half space was such that all the weights were polynomial in size, then you can sample from f inverse of 1. Okay.
Just because, so the marginal probability of like a particular beginning of your string x would just be determined by some number in some polynomial range.
Kind of, yeah. Yeah, kind of, yeah. Okay, so what Dyer says is, of course, in general, the half space might have exponentially large weights. So what you do is you round the numbers up, so that you round the numbers, you create another half space G by just rounding the numbers up with the such that this new half space G has two properties. New half space G has only polynomially large weights. Every satisfying assignment of f is a satisfying assignment of G. Those two properties individually are very easy. I mean, those two properties are easy to achieve, just the all ones half space or something. The third is that G has only polynomially many more points than f does. Okay, so 3 properties. Now you have G explicitly, so you can sample from G inverse of 1 because, well, G has polynomially large weights. And then you can just filter according to whether it's a satisfying assignment of f or not. Because it's dense, you can do rejection sampling. So dynamic programming for the first part, rejection sampling for the second. That was the algorithm of Dyer. So G is you had f explicitly. So you just round the integers up, like you round them up, you scale them. Yeah, so it's a easy, but it's Yeah, but it's not a hard proof. It's like a simple 3-line proof, but it's a crucial point. That adds only polynomial. Yeah, it multiplies only. So early, if f had like p fraction of points of the hypercube, this will have n cube times p fraction of points of the hypercube. And you can do reduction sampling. as in multiplies. Okay, so this is the algorithm of Dia. Okay, okay. So now you need to learn f in some sense. What sense do we need to learn f in? Okay, so standard so standard senses of learning are not sufficient. Okay, so for example, let's try what sense can we learn f in. So one notion might be the standard pack learning under uniform distribution, meaning suppose you manage to generate a suppose after seeing this positive assignments of f, uniformly random positive assignments of f, you manage to generate a hypothesis such that on the uniform distribution hx is not equal to fx with probability bounded by epsilon. Okay, is this notion sufficient? The answer is no. Yeah, because maybe almost everything is rejected, because it might the real hard case is that f is very sparse. So f has only, let's say, 2 to the minus n over 10 fraction of points. H has maybe 2 to the minus n over 5 fraction of points. So of course this is almost always 0, this is almost always 0, so they almost differ, almost are the same. But the L1 distance between uniform on H inverse 1 and F inverse of 1 might just be very close to 1. Okay. So if you just learn F in any standard sense, it's difficult. Okay. What you need to do is, what you can say certainly is that if this hypothesis does hold good, what does get implied, however, I don't know if, is this legible because of all the chalk? What is, however, true is that you can say that the uniform of n on H inverse 1 and uniform on F inverse 1 differ by epsilon divided by the density of F. Okay. This, however, is true. This is very easy to see, really. I mean, if Hx is not equal to Fx, then you can easily show that this, yeah. Okay. So what you need to do is to learn F in this multiplicative sense. You need to produce a hypothesis H such that H and F, instead of differing, let me use a different colored chalk. Instead of differing by epsilon, oh, this is a bad idea. Okay. Instead of epsilon, it's epsilon times F inverse 1 divided by 2 to the n. This is the kind of error we would like, a small multiplicative error. If we can achieve this, then here this will become epsilon. Okay. Okay. Another subtlety is, of course, even if you achieve a hypothesis H like this, it's not immediately clear what you can do, because as I said, sampling from H might be a very difficult job. I mean, if H is not a half space, if you don't end up producing a half space, you may not be able to sample from H if it's just a polynomial size circuit. But at least let's try to meet this thing and then see, hopefully we'll come up with a half space and hopefully we can go from there. Okay. So is the notion of multiplicative error clear? No? Why do we need multiplicative error? Okay. So not doing well on time. Now I'll have to manage the board space a little better. Okay. So what we want to produce is a hypothesis H meeting the following standards, right? That meeting the following requirements. The multiplicative error I can rephrase in the following way. that if I draw x uniformly from f inverse 1, then hx equals 1 with probability 1 minus epsilon, and probability, if I see the set on which fx is 1 divided by the set in which hx is 1, the relative sets of the relative densities of these sets, that better be at least, let us say, 1 minus epsilon. Okay. Of course, it is going to be bounded by 1 plus epsilon because of this kind of a constraint. But so what I am saying is that you can translate that multiplicative error into these two conditions, that almost on all satisfying assignments of f, h is 1, and h is 1 on not a h is not 1 on a huge set. So maybe, I mean, this condition you can just achieve by making h uniformly 1 on the whole hypercube. You want to make sure that the set of satisfying assignments of h is not too larger than the set of f. Okay. So we want to, this is what we want to do. Okay. So suppose we went, even if we relax the second criteria. Okay. So suppose instead of dealing with this thing, suppose we dealt with, we relax the second criteria. And sorry, mu of h, yeah, it's easier. Okay. Suppose I relax this criteria and say it's at least 1 over n to the 10. Okay. So something something not exponentially small. Can we achieve this thing first? This is what we want to achieve. Can we at least try to achieve something much weaker? Okay. So as usual, there are two questions: A, can we do this? B, even if we do this, how is it helpful? Okay. So as I did earlier, let me try to answer the second question first. Even if we achieve this weaker thing, like if we learn f in this weaker multiplicative sense, can we achieve this stronger multiplicative sense? Okay. Okay. So let me actually try to do it here, because it's not. So suppose we achieve this criteria, and it also happens that h is a half space. Okay. Then certainly we can, point 1, because of Morris Sinclair, we can certainly sample from uniform on h inverse 1. Technically that is not true. You can only sample from distribution which is super close to h inverse 1, uniform on h inverse 1, not uniform on h inverse 1 per se. Dyer's algorithm can actually be modified so that it's actually this Las Vegas algorithm, meaning that you can, when you sample uniformly from h inverse 1. Okay. Now suppose now you work hard and you get a hypothesis like this, that you produce fx not equal to gx, you produce a hypothesis G such that this happens, then it will imply that then it will imply that uniform, I'll explain what I'm doing here. You don't have f. No, I have, I mean, first of all, I haven't obtained h. I'm saying even if you obtain h, You sample from H inverse 1, you do not have F. I am trying to learn F. Sorry.
So yeah, I'm not. Yeah, I don't have this kind of. Okay.
You don't have. Okay. But I am saying. I'm saying you can certainly sample from H inverse, so uniform on H inverse 1. So, what was the basic problem? The basic problem was that F is super sparse. F there is a possibility that F is super sparse. F is only 2 to the minus n over 10 fraction of points of the hypercube. If you are given such a hypothesis H, then explicitly, then you have something in which F is dense. F is 1 over n to the 10 dense. It is polynomially dense. Now, if you can learn F under the uniform distribution on H inverse 1, if you could have learnt F with error epsilon, then it is like easy to show, just like the 2-line of algebra, to show that the uniform distribution on H inverse 1 intersection G inverse 1, so G is your hypothesis by which you learn F, differs from F inverse 1 by epsilon times n to the 10th, okay? Meaning that you need to learn F inside this uniform distribution H inverse 1 with only a polynomially small error. You can just learn it instead of epsilon over n to the 10th. Does this make sense? So, basically the basic issue was F was very sparse. Somehow we managed, if we can create a function inside which F is dense, and also that it captures most of the satisfying assignments of F, then you have created, in a sense, like, not a proper word, but you have densified F. And now if you have densified F, then you can learn F just inside this distribution. You can produce a hypothesis, and then this distribution H inverse 1 intersection G inverse 1 will differ from F inverse 1 by very little. Yes, that is a new hypothesis. The question is, can you in fact sample from this distribution? And the answer is yes, because if H is a half space, you can sample from H inverse 1, and then you can just reject or select according to G. And well, I mean, if F is dense inside H, F and G differ by very little, then G has to be dense inside H. So you can reject or select according to G. So you can also sample from this. That's a principle of sampling, and here we are using the same principle to do learning.
Okay, so I have a very naive question in terms of learning that I think about it. What's wrong with just bootstrapping the sample that you have? So you want to simulate, you want to be able to generate samples from uniform on the
F inverse 1.
on F inverse 1?
Yes.
And you have a bunch of samples that are from uniform on F inverse 1?
Yes.
So why can't I just pick at random from the sample?
Sorry.
With replacement?
No, you want to produce a circuit.
Samples from this uniformly at random. What you do is you say take the sample and generate one of them at random, then you are generating a uniform distribution on a completely different set that has nothing to do with the initial distribution. It's just on the sample.
So I have poly-n samples, right?
Yeah.
I number them from 1 to poly-n,
No,
and then I make a uniform distribution 1 to
and this
poly-n.
distribution is uniform on the sample, which is very far than uniform on F inverse 1. The distribution on F inverse 1 is on, let's say, 2 to the root n points. Uniform on some 2 to the root n points. And you are generating another sample, which is the distant one.
I mean, you will never produce a sample which you have not seen. Here, I am going to produce a circuit which. Yeah. Yeah. Okay. So yeah, as you said, like the basic principle of even Markov sampling is when this set is sparse, you somehow try to find a set inside which your original set was dense, and then you do rejection sampling. This is one of the principles of doing sampling. And here we are using the same methodology to do learning, that it was difficult to learn F when F was sparse. So somehow if we could work hard and make F dense inside an explicit subset, then we could learn F in the right sense, in the multiplicative sense. Okay. Any questions? Okay. So of course I haven't said how do you learn F, how do you learn a half space inside an arbitrary distribution. Remember, one hand is tied behind our back, so like we only have.
He's basically trying to do rejection sampling inside H-1, right? Only you have to do it in a clever way.
No, first you need to learn what f is.
Right, yeah, so for this you need this G.
Yeah, so you need to get G first of all. So I haven't described how do you learn G. I mean, so far I haven't used any learning really. I've only been going from one distribution to the other. Okay, so also remember, half spaces are super easy to learn just because of linear programming. If you get positive and negative samples, half spaces are super easy to learn. The issue is that we only have, and under any distribution, the problem is that we only have positive samples. How do we learn f? Inside this distribution H inverse of 1. So you can generate samples from H inverse 1, but it's still a fairly arbitrary looking distribution. How do you learn f inside this function distribution with only positive samples?
It's up to you, but you can take a 5-minute break.
I'll do it right after like 2 or 3 more minutes. Yeah, I think like there'll be a good stopping point also like at this point. Okay, so I haven't done 2 things. One is how do you describe H? How do you find out H, which is the harder part? And if you are given H as a half space, how do you produce the hypothesis G? How do you produce a G? Okay, so let me try to do the second thing first. It's much easier. I'm always doing the second thing first. Maybe I should reorder the way I think. Okay, so you only have positive samples. You do not have negative samples. You cannot do linear programming. I mean, you only have positive samples, so you can't say separate the positive from the negative. Okay, but there's something you can do. So for this, I need to introduce a terminology which is called statistical query learning algorithm. Okay, so statistical query learning algorithm is a broad class of learning algorithms for learning functions, and essentially everything which doesn't do linear programming or solve GF2 equation or solve linear equations is statistical query, which means the following. In a statistical query learning algorithm, you assume that the learner doesn't necessarily have samples from positive and negatives, doesn't have labeled samples from the distribution. Instead, what the learner has is that the learner can make statistical queries to an oracle, which means the following. A statistical query is defined by a function chi, which takes -1, 1 to the n, -1, 1 to this. Okay, it's labeled by a function chi, and this chi can be anything which is computable in polynomial time. So the learner can give an oracle any chi which is of this form, like a function which takes this and is of polynomial size, and the oracle is supposed to output that if the underlying hidden distribution is D, the oracle is supposed to output chi x fx. The learner is supposed to output, the oracle is supposed to output a number nu such that nu is a very good approximation of expectation of chi of x comma fx under the hidden distribution D. Okay, and this tau, you should think of tau as something inverse polynomial. So tau is a parameter that goes to the oracle. So almost any learning algorithm many learning algorithms are statistical queries. So anything based on like Fourier analysis or anything is like statistical query, because in particular this can simulate a correlation with any function. So any algorithm which says give me correlation with this function, give me correlation with that function, and then gives a learning hypothesis, that's a statistical query learning algorithm. Is there no notion of statistics?
There's no limitation in the order of the correlation measures?
Or order? Yeah, allowed to. So chi has to be a polynomial time computable function, and also you can give only polynomially many queries, and every answer may be returned with some error tau. This is also a parameter. Think of it as like inverse polynomial in n, and you can make only polynomially many statistical queries. Okay, why am I talking about statistical queries here? The point is that if you have access to uniformly random samples from f inverse 1, and you have, so here we are trying to learn f under this distribution uniform on H inverse 1. So the underlying hidden distribution is H uniform on H inverse 1. I will show, basically it's 2 line of algebra to show that any statistical query can be simulated if you just have access to positive samples from F inverse 1 and the value of how dense is F inside H inverse 1. We do not have that value, but for the moment just assume you have that value. Later on we will do some hypothesis testing to figure out what is the right value. We will try over many possibilities. Okay. So, I am saying basically that if you just have uniformly random samples for F inverse 1, then you can get a pretty good estimate of this number. Okay. And the reason you can get a pretty good estimate of this number is the following two line really. Is equal to expectation of x in D chi x minus 1 plus probability f x equals 1 under x in D times expectation of x f x equals 1 x in D chi x1 minus chi x minus 1. Okay. So, I am saying you can verify this algebra is true, it is not hard to show this, I mean this is true identity. D for us is uniform on H inverse 1. So, we can sample from H inverse 1. So, given any function chi, we can calculate a very good estimate for this number just by doing sampling. We are assuming that I have been told what is the I am assuming that we have been told what is the density of f inside H. Just assume that number, will later go over many possibilities, and then this is saying chi from f x equals 1 chi sampled according to D. And the point is that again this is, you readily have samples from f inverse 1 and you can just decide whether they fall in H or not. So, you can get this distribution as well, and then you just need to evaluate this function chi. Moral being, given positive samples from f inverse 1 and the function H, you can get values to any statistical query up till arbitrarily good errors like polynomially small errors. So, you can simulate any statistical query learning algorithm inside F. You can simulate any statistical query learning algorithm with positive samples from H inverse, with positive samples from F. And the one line thing is that half spaces can be learnt using statistical query learning algorithms under any distribution. This is a result of Blum, Fries, Kannan and Vempala. I do not know the proof, so I can't help really what happens. So, since we have access to H, we can simulate statistical query learning algorithms and we can produce a hypothesis G. So, really the only task left at this point is to get the function H.
How do you know the density, the very good estimate?
No, we do not. So, we will try over many possibilities. We do not have any idea, but
because of the same reason you can estimate whether your guess was right.
No, sorry.
No? The density of f inside H.
Yeah, how will you do that? You have H, but how will you estimate the density of f inside H?
You are learning, so for each such density you are learning some G. Right?
For each such density we will learn some G, yes. And then you will have several possible candidate distributions, one of which is close to the target distribution. The point is that if I am given several candidate distributions and one is the right one, you can do this thing called hypothesis testing. It is important what form I have been given this candidate distributions. If I am just given circuits for the candidate distributions, this problem is I think in SDK or something like that, so it is hard. We are given we can actually evaluate probability densities. So, if you are given several candidate distributions and you can do probability, you can get density as in form of you can evaluate the density of all of these candidate distributions, and there's some candidate distribution to which one of this is close, you can say which one. Okay. So, you don't know the density, but we'll go over all possibilities, and that's really the reason. And so, all that remains to be done is to learn H or get this H. I think this is a good point for me to stop, take a break, and questions.
So it's not possible to try to find the, it won't work, or it's not computationally efficient to just try to find the linear space that puts all the one that's the
tightest, like some pushes as much as possible. No, I think that's NP hard.
Okay.
Yeah, I do not know a proof. At some point, I thought this was well known. This was known, but
Something that satisfies all the positive and contains the minimum number of points.
Essentially, yes.
I thought at some point there was a known result saying that this is hard to approximate even up to like minimize the points up to like even polynomial factors was hard. I couldn't find the result yesterday, but I certainly my intuition is that this has to be very hard. Like putting geometrically finding the tightest half geometrically or like in terms of these numbers the tightest half space, that has to be very hard.
So actually, I'm still not convinced that my idea doesn't work, because so here your problem is when you're the support of f inverse of 1 of f minus 1 is actually really sparse, right?
No.
Can be 2 to the n over 10.
2 to the n over 10. It's sparse as in over the whole hypercube. It's sparse. It's not sparse as in the only 50 polynomial. Yeah, you will just see all the samples and then you will start seeing repetitions. And that point, you can say it's fine. It's sparse, but it's dense. It's enough so it's to cause you trouble. No, I thought it was. I mean, okay. I mean, natural is like a subjective matter. I felt it was a obvious question to ask, like, what are the low complexity distributions you can study? And okay, so this was essentially how we arrived at the model.
I have a vague machine learning application for that, which is anomaly detection. So let's say you observe only non-anomalous observations, so normal observations. You have a machine that produces something that works, and you want to know eventually what does something that doesn't work look like, but you've never seen it.
Actually, this is this kind of a model. When we're like looking for references, there's something that's used somehow related to something in learning languages. In a sense, when you are learning a language, you only see positive examples. You don't get to see like this is blah is not a valid word. Also, this set is a very sparse set, right? I mean, in the set of languages, the set of the lexicon is a very small set. So, in a sense, yes, it's somewhat motivated. I mean, the algorithm just came out, so
The learning the distribution though is a little more tricky, right? I mean, from a learning point of view, it doesn't really make sense to. Why would you want to generate more instances? In a way, you would assume that nature would do that for you, and all you need is the function that tells you when it's going to be 1 and when it's going to be 0.
Well, it's doing that. I mean, okay, in a sense,
Most of your work is beyond
most of the work is actually getting the function right, but well, whenever you're trying to do this, one issue is that if you say there is the function, then you have to also assure yourself that there is the function. Like there cannot be two functions which are.
You can think about it even as an intermediate step of learning the half space, but with this new guarantee, which is right, it's not the standard guarantee that you use in fact. You learn it with a much higher accuracy. This multiplicative thing. This is a goal in itself. It's just learning a function.
Yeah, I mean, in general, when you're given a half space and it's very, I mean, in general, you can never have multiplicative errors because, well, you may not get to see the small part. Now you get to see the small part. You should have a fair shot at learning the small part. And
So you can pretend to speak German without actually learning German, because you will be able to put
More German words.
Good for the Chinese room experiment.
Yeah.
What if it is a roughly uniform distribution on the inverse of that?
Okay, so I think mainly the issue, as we'll see, okay, so far really, I mean the next part I'm going to do how to get h, and it's again going to use this Morris-Sinclair algorithm over and over again. So I think I'm not saying this as a mathematics as a theorem, but I feel the only distinction like what we require it's uniform on f inverse 1 is your ability to sample from the uniform satisfying assignments of f inverse 1. You can say consider like you can consider something else like roughly uniform on f inverse 1, but provided you can sample from this roughly uniform on f inverse 1, I think the algorithm should just go as it is. I think really the key thing which allows you to learn certain things and not learn certain things is this, well, it's no longer on the board, but the ability to sample from f inverse 1. I think that's the key point. Like if you can sample, you know, it's, I don't think it's formally as a I don't know in what level of generality. I don't think it's formally this is true for any like all classes or. Yeah, it's not. Yeah, so I do not know. Like I mean, also like you reach what cannot be learned pretty quickly, right? CNF, so monotone to CNF, something super trivial cannot be learned. So. If you could have learned, you can definitely sample. I don't know, formally I don't see why this has to be true. And I'm sure, you know, graph isomorphism was the right example. I just can't remember the setting. There was an example we wrote in the paper, but I just can't remember the. Yes.
Do we know how to learn half spaces when there's noise in the observations?
Sorry?
It's a purely back from. Do I know how to learn half spaces efficiently? If I so just the function. If I observe noise every time instead of getting 1 or 0.
Everybody understands.
Okay, so there are two things I can actually do now. One is try to okay, I'll definitely do how to describe how to learn h, how to do this, how to learn h. One is I can try to motivate the learning algorithm a bit more, and another is I don't motivate. I just get to directly to the algorithm that works.
Actually, I think you should motivate it.
Okay.
Knowing what you are going to say.
Okay. Okay. So we want to do. Okay. So maybe I'll just end up just doing the half space thing, and we won't have time for anything else. But that's all fine. Okay. So we want to produce a hypothesis H meeting those guarantees. Okay, Hx is greater that on almost all positive assignments of f, H is 1, and that H is not too large compared to f. We want to meet those two guarantees. The first guarantee is super trivial really to achieve, namely you have access to f inverse 1, right? So sample n, let's say n cube. I actually have the numbers written down, so I don't want to fumble later. Let's say xt from f inverse 1, where t is order, let's say n cube over epsilon log 1 over delta. Okay, and it's easy to prove that if H is any half space such that for all I in t H xi is 1, then probability in x inverse 1 Hx equals 1 considering 1 minus epsilon with probability 1 minus delta. So I'm saying Meeting the first criteria is super simple. Just sample random n square or n cube of epsilon points from f inverse 1 and just give me any consistent hypothesis, any half space which labels all these points as positive. It has to be the case that H is 1 almost on all of f inverse 1. This is this is the key, the union bound, basically a number of half spaces 2 to the n square. You can just do a union bound. And this is not hard. I mean, of course, H equals 1, always 1 would have done this. So really the key part is getting the second argument, okay? Okay. So second on the right, the second that density of f is large compared to density is reasonable compared to density of H. Okay. So we can probably say something similar about negative points. Suppose in a hypothetical world you had lots of samples. Okay. So suppose you had lots of negative points. Okay. Suppose you had access to negative points. You don't, but suppose you had access to negative points. If you could have sampled n cube over epsilon times mu of f inverse 1 negative points from f inverse minus 1. So, you could have sampled these many negative points and output a consistent hypothesis. If you could have output a consistent hypothesis H such that all these points are marked negative, then you would have met the second criteria as well. Again, the same reason, there are only so many half spaces. There are two issues with this. One is you do not have negative points. The bigger issue is that this number is huge. I mean, this number is huge. I mean, this number is potentially huge. So, even if somebody gave me negative points, what do I do? The first issue is somewhat easier to tackle, and what I'll do is I'll just say the following. Choose a random set S of okay, so first issue is easier to handle. You can't do this, but suppose you just chose, you can't do this, but suppose you just chose 1 over n to the 10 times mu f inverse 1 points from the hypercube. Then with high probability, with probability 1 minus 1 over n to the 10, all these points will actually lie in f inverse minus 1, f inverse of minus 1. This is basically because that this is the density of positive points. So, you are choosing something substantially smaller than the density. So, almost all of them points will lie on the opposite side. Okay. Of course, again the same issue persists, you can't do this, but then you can show that if you could have done this, then okay, I do not want to erase that. So, sorry, I will have to keep erasing this part. Actually, is it okay if I write here? Okay. Then you can show that if you sample S, these many points, and find a hypothesis which labels all these points as negative and well the positive points as positive, and call that half space H, then with high probability both the following criteria will be true. Probability of H equals 1 will be okay, probability of H equals 1 will be bounded by n to the 5 times probability of H equals f equals 1 under the uniform. Yeah, if you do this thing, you solve so you sample these many points and these many points, you solve a linear program. The first criteria there will be met, that is always easy to achieve, and the second criteria will also be met, that the probability that H is 1 is at most n to the 5 times probability of f is 1. This is what we want to achieve really. Right. Okay, so the only issue that persists is that we can't sample so many points. But what should come to mind is that, well, we have a linear program. So even there are exponentially many constraints. If we could have defined a polynomial time separation oracle, we could solve this linear program. Yes.
Do you assume you know the density of
Yes. So again, we are assuming here that I know the density of f inverse minus 1. As before, we'll get rid of this later. So the issue is that, okay, the first answer is, okay, if you could have constructed a polynomial time separation oracle, we would have been done. The only issue here is that, okay, the only thing is, how do I construct a polynomial time separation oracle? The linear program is not even explicitly defined here. We are just saying sample random points. So like the dual is something random. I'm not quite sure how to interpret the separation oracle here, because it's a random set of constraints. What is going to be helpful is kind of that it's a random set of constraints. Okay, so we are going to use the fact that it's a random set of constraints. I do not know how to interpret the subsequent algorithm I'm going to describe as a separation oracle, because it's a random set of constraints. I'm not sure what the dual is supposed to look like, but we are just going to solve the linear program. Okay. Okay, so which part can I erase? Which part is okay to erase? No. Let me just erase this. Okay. So we are going to look at the ellipsoid algorithm as a two-player game. It's a useful formulation to think of. Okay. So the ellipsoid algorithm is an algorithm for solving linear programs, and we are going to think of it as a two-player game. Alice and Bob. So assume Alice has a bunch of constraints, and she doesn't know how to solve the linear program. Bob is running the ellipsoid algorithm. So here is how we can think of the guarantee of the ellipsoid. Bob is initially going to say, give a solution, give some x, and ask Alice, are all the constraints getting satisfied? She is just supposed to say yes, in which case they have attained the solution, or she is supposed to say no, here is a constraint which gets violated. Then Bob is going to run ellipsoid algorithms as one step of it, and going to output another point and going to ask, does this work? She's supposed to say yes, or here's a constraint which doesn't work. And the guarantee is that this game, ellipsoid, I don't know the running time, but let's just assume that after n to the 5 rounds, it's supposed to be something more, n to the 20 or something, but the guarantee is that after n to the 5 rounds, either Alice will end up with a point with a satisfying assignment, or Bob can certify there is no satisfying assignment. The system of constraints in this case. She can generate any constraint. Ellipsoid doesn't care what. She will generate random constraints. The point is, Alice can generate random constraints. Bob has to do all the smart things, but Alice can generate any violating constraints. Okay. So now think of running this game. We are trying to solve this linear program. We'll streamline the algorithm a bit so as to make it quicker. So we will of course simulate both Alice and Bob. So so first we will just sample x1 to xt from f inverse 1, where t is n cube over epsilon. Okay. So initially we are going to run Bob's part, and we are as Alice we are going to check, hey, are all the positive points being marked positive? If not, we will just return one of these xi's to Bob saying this constraint is getting violated. This will go on for a while, and then at some point Bob will return a hypothesis, a half space hypothesis, and now maybe all the positive points are getting satisfied. Then as Alice we will check the following: what is the density of the hypothesis Bob has returned? We can do this because random sampling and approximate counting are equivalent. So you can, given any half space H, you can compute probability of Hx equals 1, x in uniform, up to very good error like 1 plus minus epsilon error. Okay. Multiplicative error. We will see what this number is. If this number is at least, if this already this hypothesis is getting satisfied, we stop the game. We don't care to solve this game. We don't care to move forward. So, we can stop. If not, then I know that at least the density of H is at least n to the 10 times the density of F. Hence, if I sample a random point from H inverse 1, which I can again do because of Morris-Sinclair algorithm, that point with probability 1 minus 1 over n to the 10 is a valid negative point, is a point which is marked negative by F. So, as Alice, we can return this point. This is a valid step, and I know that provided all the steps are simulated correctly, n to the 5 is an upper bound on how many times this thing can run. So, and every step I know is being correctly simulated. Either I stop, in which case I am good, or I simulate one step of the game with probability 1 minus 1 over n to the correctness 1 minus 1 over n to the 10. This can run for n to the 5 rounds. So, simulate every step of the game correctly with probability 1 minus 1 over n to the 5. Thus, when I stop, either I have gotten like F itself, or I have stopped where I have gotten H.
How do we know that the volume of H decreases all the time quickly enough?
No. So, this is we are using the ellipsoid algorithm. So, this is the tricky part, that we are using ellipsoid to show that the volume of H is decreasing rapidly.
You don't actually explicitly say.
We don't explicitly say it. I do.
Yeah.
Yeah.
You use the black box, the property that the running time of the ellipsoid algorithm or the number of rounds is so much. And these are valid steps in the ellipsoid algorithm.
Yeah, I mean, I do not explicitly know how to argue this, guarantee this part like by just like first principles, but the fact that ellipsoid algorithm works correctly says that provided any time I am moving a step, I do not even know every time I am making a progress or not, but certainly I will stop the game within n to the 5 rounds.
It works correctly. I need that the violated constraint every time will be violated by
Is a correct
No,
constraint.
not by a lot. Not by a lot.
No, not by a lot.
Not by a lot. Any violation, any separating hyperplane is good, which is this what we do.
Any constraint is good, and the only time I actually, I mean, either I am always returning constraints from this, which is great, or the only time I move forward with a.
You don't have to make it so mysterious. You are giving a separation oracle. The separation oracle is run Morris-Sinclair and get a point.
Yeah, I mean that's true. That's true.
It is a separating hyperplane which works with very high probability.
But it's not that okay. So separation oracle works. Okay, you are correct. Separation oracle is working, or I know I'm already stopping. So one of the two things. Either the separation oracle is working, or
Assuming you are still, the volume is still too big, then you get with high probability separation.
exactly. Okay. So this is a separation oracle. This is a separation oracle. So the only time you will move, either you stop or you move one step of the algorithm which is correct, and you are using ellipsoid to justify how quickly the thing is, like actually you are making progress. Okay, that was the proof. Questions? Yes.
Here you use the ellipsoid method to actually bound the running time, but is there a sense that if you went from first principles, you might decrease the running time?
I do not know how to go from the first principles. I do not actually know. I mean, one potential thing is that maybe one can try to prove that at every step one is making substantial progress, like reducing the volume, which is something ellipsoid does. I mean, ellipsoid is implicitly when it cuts down the size of the ellipsoid. It cuts down the size of the ellipsoid algorithm, cuts down the size of the ellipsoid, not necessarily this set. So I do not know if the following can be proven, that at every step I am cutting down the size of the positive set of H by some non-negligible quantity. Ellipsoid argues that you are cutting down the size of the ellipsoid. I am not sure what the one-to-one correspondence is between. Is there a correspondence between those two sizes? Making sense? Excellent. Excellent. So, okay. So, CNFs, unfortunately, CNFs is DNFs. Let me talk about DNFs for a bit. Okay. So, any questions here? Or this looks fine. Yeah, it was indeed important that we can generate also that we can approximate the density. So, which was also like a consequence that you can generate. So, this approximate counting random sampling. So this is the only step which seemed like over and over being used over and over again. The fact that more single algorithm was there. This was the only.
In also example, so here indeed your hypothesis, so the H would also be a half space, although it could have been something else.
It could have been something else, but here H is also a half space. It was lucky that H came out to be a half space. If H was not a half space, we would have been in trouble. Okay, so yeah, I mean the only step which I did not discuss was how do you get rid of these probabilities. You don't know the probabilities, and the point is that you can go over all possibilities, and if you are given several candidate distributions and one target distribution, you can decide which one is the best hypothesis, provided you can evaluate probability densities of all the candidate distributions. That's the true statement. There is nothing.
You have some sort of approximation algorithm, so that's a subroutine of your results. That if someone gives you some positive examples for a half space and tells you that this half space is not does not contain too many points, you'll be able to find a half space that does not contain too many points. So maybe not more than n to the 10 times this, and also it's positive and all of that.
Yeah. Almost positive, almost on all of. Yeah, but it is using the fact that you got n to the 10 random points.
Yeah, but that's fine. I mean, you could.
Yeah, I mean in the sense that you got okay. So the no. This problem so I maintain my statement. So what you got when you got the positive points from F, they were random. And always everything was underlying distribution was uniform. So in the adversarial case, if I just gave you like some bunch of points which were adversarially chosen rather than uniformly chosen from F inverse of 1, I'm not sure how to do this algorithm. And
so you're saying suppose we're considering this approximation problem. So given a bunch of points, vertices of the hypercube, you want to find a half space that contains all these points and contains a minimum number of.
Yeah.
Okay, and suppose you apply something like this, you're saying that this will not give a good approximation.
So one thing that went into yeah.
Because it doesn't really matter what you got at the beginning. I mean later you will get.
No, but I did use the fact that the points you got were uniform on F inverse 1. What if I gave you points which are all from F inverse 1 but are like adversarially chosen?
Okay, but then my algorithm will generate some H and then let's say they are adversarially chosen, but you know also what the density of F is.
Yeah, sure. Sure. Let me also know the density of F.
Okay, so where did we use actually that the original points were also random?
Just in guaranteeing the easy first part.
The easy first part. The easy first part. It used that. Also, like it.
No, I mean, the first part is by definition. Because we are asking, so I give you positive points.
So let me give you an example. Maybe you can think about it in this context. So it's the whole cube. Your half space is the whole cube. But I gave you just a 0 point.
No, but you see, what is the problem I'm trying to solve? I'm trying to find the half space that contains all the points that you gave me and a minimum number of other points.
So there is no distribution.
No distribution, yeah. I mean,
So
the worst case thing. But I'm saying that you are solving this problem, right?
I'm.
Because by definition, I mean, you have some set of points, and we want a half space that contains all these points and has the minimum number of additional points. Okay.
No, it's not.
No. I think what you are using is that the points you chose kind of identify the half space robustly. I may give you satisfying assignments of half space which do not identify the. They define but do not. I don't know.
They define. Yeah, I understand.
Plus, like okay. Okay, it's not clear it doesn't work. Also, for the union bound to go through, I required like some or the VC dimension, something like that. I would require blah number of points, like n cube or n square, something more than the number of half space, total number of half spaces of the hypercube. In between, if I give you 1 to n to the 1.5 points, maybe I didn't give you it. So that is also like sometimes this is certainly playing a role here. I do not know how it will.
So it's a question,
When it's adversarial, there is no meaning to this half space business.
No, but I want to. So we are looking for the half space that contains a minimum number of points and contains all of those.
That's it. This is the problem.
This is It contains all of almost all of those, and
It's a problem. So you can define your distribution to be uniform
on these points.
Given, but there has to be a subspace containing exactly them for this to work.
Containing them and containing the right density. We don't know what's the density of the solution.
Well, I don't see that.
Yeah, I don't see that.
Yeah, exactly.
And what about the other points? No, you still can't solve the linear program. Like even if all those points and.
But at least it's not clear what. So it's clear that this algorithm completely fails miserably on this on the worst case. Someone gives you a bunch of points, asks you to find a half space containing these points and containing the minimum number of additional ones. You kind of run your algorithm and hope.
I know. I don't know. No, the answer is no. I mean, it seems like it might actually work or give something meaningful. It might give something meaningful. I mean, one question is, as I said, I mean, maybe it doesn't identify the half space uniquely or some robustly, like the first guarantee. But then there's a question to ask, like, do I care? Or I mean, why is it so critical? Yeah. Exactly. I do not know. Okay. I mean, at some point I thought it miserably fails, but now I'm no longer sure in the last 10 minutes whether it's actually true that it miserably fails. Maybe it works.
But you said that maybe it's known, maybe there is some hardness.
Yeah, I thought when we were first thinking about this problem, I mean, the first guess was like find this tightest half space, and then I think Rocco came up with a reference saying that this is hard, but I was trying to retrieve the reference 2 days ago and I couldn't find the reference. So, and neither could he. So I'm now like maybe we saw the wrong thing. Certainly.
Yeah, you're saying essentially this is the optimal classifier, and so if we're actually able to learn this thing, then it means that we can actually approximate this guy at least up to some constant, right? So yeah, but we can do some approximation at least of this problem. But
No, it's a legit question. It's a very legit question. I do not know the answers. I do not know at this point. I do not really know.
Actually,
yes.
I have you brought up VC dimension. I was asking myself a slightly unrelated question. Is there a notion of VC dimension when you restrict the points that you're trying to shatter? Well, the points that can shatter your set of sets to be on the vertices of the hypercube.
Sorry, VC dimension.
So you know, for VC dimension, you have a set of sets, and you're trying to say, well, any configuration of you can shatter them with any configurations of points in RD, right? And here you constrain your points to be on the hypercube.
Yeah.
And so, is there a notion of VC dimension for this? I mean, does it differ from the usual notion of VC dimension?
VC dimension is defined for any abstract hypergraph, so you can define it for the set of vertices with just the vertices.
No, it just asks but whether this number will be smaller. In this case, where
Is it D? So VC dimension of half spaces in general in D dimension is D.
Yeah.
And the question is if you do it with plus minus 1. I think that yes, because anything you take just linearly finally independent points.
For half spaces, yes, but do we know any examples for which it might not be the case?
There must be.
Yeah.
I don't know. I don't know. Okay, so I guess I have 15 minutes.
Yeah.
Is that okay? So let me just say without writing too much math as to what happens in DNFs. Actually, I will eventually start writing. So let me. Okay, so.
You promised to
Good. So 5 minutes about DNFs, 10 minutes about hardness. I don't have much to say about the hardness. It's hard. Like yeah. Yeah. I mean, it's like a trivial hardness reduction. The hardness reduction is not hard or anything super interesting going on. Okay, DNFs. Okay, so DNFs again. For the problem for DNFs is that you have these DNFs. You are getting random satisfying assignments of a DNF, and you want to learn this. You want to learn the satisfying distribution. You want to learn the distribution uniform on the hidden DNF. Let's see what we did in the earlier thing. Earlier, we first created this for half spaces. We created this, kind of a not an English word, but densifier, this function h, and then we simulated a statistical query learn. We said that half spaces can be learned with statistical query learning algorithms over any distribution. The main issue is, okay, so can we create a densifier for DNF? Well, we don't know. I mean, we will actually create one. But the second question is, do we have a statistical query learning algorithm for DNFs over arbitrary distribution? And the answer is not that we know of. In fact, even pack learning DNFs over arbitrary distributions is a terribly hard problem, and the best running time is 2 to the n to the 1/3. Okay. So how do we get around both these problems? One is, well, we construct a densifier, and B is how do we learn do statistical query learning. So the constructed densifier for DNFs is much more intuitive. The idea is that no, Luby-Karp will do the sampling. Of course, we'll again use the we'll do the Luby-Karp sample. Karp-Luby. Of the Morris Sinclair, it's a much simpler algorithm, but no, the Morris Sinclair. This is on tape. I can't say this now. So, okay. So in construction of densifier for DNFs is a much more intuitive process. What do we do when we are usually learning DNFs? We'll say, oh, this is a polynomial term DNF. So all clauses, all terms which are of length log n or larger should be discarded. Here we cannot unfortunately say that, because the challenging case as before will be when you are getting the terms are huge. But there is another interesting thing that is going to happen. In general, if I am given a DNF, or in general if I have the uniform distribution, let's say the DNF, let's say there is a clause, there is a term present in the DNF which is x1 and x2 and xn over 10, so n over 10 terms. Over the uniform distribution, this will be satisfied with probability 2 to the minus n over 10. However, when you get satisfying assignments of the DNF, you will see these unusually large terms getting satisfied with reasonably good probability. So that should give you an indication that this term or a subterm should be present as a clause in the DNF, and this can in fact be made precise. So basically, the algorithm for constructing the densifier for DNFs is just the following. Sample, you get satisfying assignments, right? So sample some log n or 2 log n satisfying assignments of the DNF with probability. So it's a polynomial term DNF. Let's say it's a S term DNF. There are S terms with probability 1 over S. So consider, okay, let the DNF be C1 and C2 and CS. Now sample, let G be this. Sample X from G inverse 1. Okay. This can be formalized very easily. This can be formalized, but you can assume intuitively that for any particular I, so let's say C1, a random X from G inverse 1 satisfies C1 with probability roughly 1 over S. This can be formalized. This need not essentially be true, but it's like can be formalized. It satisfies with probability 1 over S. So if I sample log n of this, all the satisfying assignments, sample x1 to x2 log n, all of them will satisfy C1 with probability 1 over S raised to 2 log n. Okay. So if S is polynomial, that is why you will have a quasi-polynomial running time. 1 over S to the log n, all of these x1 to x2 log n will satisfy C1. So, now try to find out the maximum satisfying assignment for x1 to x2 log n. Try to find out what is the biggest and no, sorry, I phrased this incorrectly. I try to find out the maximal common clause which satisfies, which is true in all of x1 to x2 log n. It can be shown again simple union bound that with high probability, then this will exactly be C1 itself. So, now if you sample, and this success probability of this experiment is 1 over s to the log n. Okay. So, repeat this s to the log n times, and you will have you repeat this experiment s to the log n times, and you will come up with a collection of terms which are a superset of the clause of the terms you intended to learn. And you can also show with some more filtering thing that this is actually a densifier for G. This is a densifier for G. You construct the densifier. The second question remains, how do you, so you get some G prime which is C1. You will find all the big clauses and maybe even more. No, you will find all C1 to Cs and a superset, other clauses as well. So, Cs to the log n. Okay. And the important thing to notice is that you will, you have to do something more, but I am not mentioning that here. The point is that G, it will be the case that almost all satisfying assignments of G will be satisfying assignments of G prime. B, what will be true is that G will not have too many more, G prime will not have too many more satisfying assignments, too many more meaning n to the log n. So, that is how we create a densifier. Next,
that's why you take log n.
That's why we take.
In order to make it small.
To make it small, yes. The next question remains, how do you do statistical? So, this we construct a densifier. Of course, I didn't describe all the details. How do you do statistical query learning? Because DNFs aren't. And the important thing to observe is that if you look at the satisfying assignments of, if you can generate from G inverse of 1, because G prime of 1, uniform on G prime of 1, like G prime inverse of 1. You can generate from the satisfying assignments of G prime, because G prime well is a DNF. You can use the Karp-Luby algorithm. And in this distribution, G actually looks like an OR. It does not look like a DNF anymore. It actually looks like an OR. It is a, these meta you can consider these as meta variables, and then this looks like an OR. So, you can try to use learning algorithms for OR rather than DNFs. There is an issue of noise, because even learning algorithms for ORs are not very noise stable. And then you have to observe the third thing, that even though this is an OR, there is some amount of noise tolerance, because in this whole space this is a very sparse OR. There are only s terms, while the number of meta variables is s to the log n. So, that gives you some sort of a noise stability if you are trying to learn sparse disjunctions versus arbitrary disjunctions. In a nutshell, this looks like an OR. So, you will use a learning algorithm for OR, and you get noise stability, because you will require some noise stability for everything to work. That comes because this is a
uniform satisfying assignments of G prime. So the clause of G prime that is satisfied is not uniform, right?
Sorry.
Bigger clauses have R1 more often than small clauses in the satisfying assignment. So I'm saying it's not exactly like
distribution.
but it does not. Okay, so it does not behave exactly like OR.
No, it is not an OR on the uniform of anything. No. I am saying consider these as meta variables. Okay, you have C1 to Cs to the log n explicitly. Okay, consider them as meta variables, not meta variables. Just consider them as variables. Okay, and now uniform on G inverse 1 is a distribution on these variables. It is not uniform on these variables, on this s to the log n dimensional hypercube. It is not uniform. It is far from uniform, of course. And you are trying to learn an OR over these variables, and you get a very necessary amount of noise stability, which is crucial, by just observing that this is a sparse OR. This is sparse in the number of variables. So, you get, because you need noise stability which is 1 over s and not 1 over s to the log n. Trivial OR learning algorithms have a noise stability of 1 over s to the log n rather than 1 over s, which is fatal for our purposes. It cannot work. I went over it in like, I went over it super fast, so sorry. Hardness. I promised 10 minutes, so you will have to bear me for 5 more minutes. Okay, hardness. So what are we trying to do? We are trying to give a hardness result, meaning what? Suppose we are trying to give a hardness result for CNFs. Let's say 3 CNFs. One trivial thing is that if you are getting satisfying assignments, so we are considering a hidden 3 CNF, we get satisfying assignments of a hidden 3 CNF. It's trivial to show by an elimination kind of an algorithm that you can learn the 3 CNF very quickly. You can just see what 3 term clauses are always getting satisfied by the satisfying assignment. So learning the 3 CNF is not difficult. Of course, now the question is, if I give you a 3 CNF, I am asking you to generate more satisfying assignments. That's of course hard. Here you have an added advice. You get more satisfying assignments of a 3. So you have a 3 CNF, you learn the 3 CNF. So now you assume you have the 3 CNF in your hands. You get random satisfying assignments of this 3 CNF, and I am asking you, is it possible to generate more satisfying assignments? And it might be, because you are getting some pretty meaningful advice. And the answer is that no, you cannot. You cannot generate more satisfying assignments of a 3 CNF given random satisfying assignments of the 3 CNF under cryptographic assumptions. And the hardness result actually comes from secure signature schemes. So the intuition is that, what are we trying to prove? We are getting satisfying assignments from some satisfying assignments of a 3 CNF. Does everybody know what a signature scheme is? Do I need to? Okay, a signature scheme is the following: that there is a signing algorithm and there is a verification algorithm. The signer has a secret key and creates these message signature pairs, certifying that the signer signed the message. This is public key, meaning the verification, anybody can actually see whether this is a valid signature. However, generating more valid message signature pairs, the one you haven't seen, is hard. This is exactly what we are trying to do. We have satisfying assignments of a 3 CNF. So if your signing algorithm was if your verification algorithm was a 3 CNF, then you will be saying, well, I am seeing satisfying assignments of a 3 CNF, the message signature pairs, I want to create more. That should be hard. The subtlety as to why we cannot prove just based on this assumption is the following. Okay, so this is the reason why this is intuitively related and hard. Okay, first of all, so if you just go and try to find out if there are signing verification algorithms which are 3 CNFs, I don't think any algorithm is written down in that way, but you can always do a reduction. You do the Cook-Levin reduction. So everything is public, right? So there is some polynomial-size circuit which is the verification algorithm. You can do the Cook-Levin reduction and make it into a 3 CNF, a polynomial-size 3 CNF, and security is preserved because everything is public. So you might as well assume that that your verification algorithm is a 3 CNF, or for that matter any NP complete language. So degree 2 PTFs, intersection of degree 2 PTFs, monotone to CNFs is a slightly difficult thing to prove, but okay. The subtlety comes from the fact that what is the exact guarantee of the secure signature scheme? It's that if I am given valid signatures, then it's hard to generate another signature, another pair which is accepted by the verification algorithm. It might be true, and it is in fact true, that the accepting assignments of the verification algorithm is a superset of all signatures. That is in fact true for most standard signature scheme constructions. And then you can ask that maybe it is true that if I am given random valid signatures, I can't generate more satisfying assignments of the verification algorithm. But it might be true that if I am given random satisfying assignments of the verification algorithm, I am able to generate more satisfying assignments of the verification algorithm. Maybe some key will get revealed, and it's also in fact true that most standard constructions will have this property. So, well, you have to look at the literature a bit, and you can find out some signature schemes where the only things that are accepted are satisfying the only things that are accepted by the verification algorithm are exactly the signatures, nothing else. Yeah, this like there's no smartness involved. It's just like go find out ask the right people, find out the right paper, and it's under some cryptographic assumption this is done.
But the hardness so indeed the hardness is on generating the distribution because learning the 3CNF is trivial.
Yeah, but learning here again, like the verification algorithm is public, so of course you can learn the 3CNF. I mean, so I wonder whether like maybe this can be proven without using cryptographic assumptions, maybe under something else. I don't know how to prove it, but some average case hardness, some average case hardness. What is in fact like, I think this is still, this is very open, is that maybe it is the case that there, even if I give you a random satisfying, maybe there is no polynomial size, even given a particular 3CNF. In the worst case, there is no polynomial size circuit which can generate which can sample satisfying assignments of the 3CNF. So, given for a specific CNF 3CNF instance phi, there is no polynomial size circuit which can generate satisfying assignments of phi. So, the circuit can be tailored to phi. It's a conjecture. It's a conjecture. Given a 3CNF phi, yeah, is there a circuit which on uniform distribution will generate a distribution close or even half overlap something? It's a conjecture, and even this might be provable under some circuit separation assumptions. I mean, I don't know. The compression, the compressible is something to do with instance compressibility or something. But okay. Yeah, I said yeah, I thought about something to do with instance compressibility maybe, but then I couldn't figure out, and not that I spent a whole lot of time on this question. But I think this is I mean, for this reason, even for this reason, it may be hard. Like whatever I'm saying, it may be hard for this kind of reason that there is no circuit which can do this. I don't know the answer, but well, that's all. Thanks. Oh. Oh, it's the same reason, because all I use for 3CNFs is that there is a Cook-Levin reduction from like any NP complete language to blah. So 3CNFs, intersection of two half spaces, degree 2 PTFs, everything. Monotone to CNFs, you have to basically go along this blow up construction which is used to prove approximate counting, and you can do the same reduction. So even though it's not an NP complete language, you can essentially get the same thing. Question? Thank you.